Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Hi, my name is Matthew Memmott. I'm an associate professor in chemical engineering at Brigham Young University and a co-founder of AlphaTech Research Corp. I look forward to sharing with you my expertise on nuclear power and talking a little bit about the nuclear and the energy industries and some of the challenges that nuclear has faced. And if you tune in, we'll talk about a great new innovation that has the potential to eliminate meltdowns, nuclear waste, and to do so at a surprisingly affordable price.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. My guest is Dr. Matthew Memmott. He's an associate professor in the Department of Chemical Engineering at Brigham Young University. And we're going to talk about molten salt reactors used in the nuclear industry and how these small modular ones are something new. So welcome. Thanks for coming, Matt.
Thanks, Richard. Good to be on the show.
Well, great. Tell me a bit about your background and what got you interested in these small reactors in the nuclear industry.
Sure. So I got my undergrad in chemical engineering from BYU, was very interested in energy engineering in general, studied a lot of fossil fuel, solar, wind, etc. My senior year, a couple of guys from Idaho National Lab came down and taught a nuclear engineering course, and I was hooked. So I did grad school from then on at MIT, got a master's and PhD in nuclear engineering, and then went to Westinghouse and worked in their advanced reactor group, led the technical aspects of the advanced reactor group, working on AP1000, small modular reactors, lead-fast reactor, basically every kind of reactor except for the salt reactor. And I mentioned it once or twice to the guys at Westinghouse, and they said, no, we wouldn't make enough money on that fuel. We're not going to do it. So it was kind of a non-starter. Well, 2014, I ended up going over to Brigham Young University to help start the nuclear program there, where I graduated from in the chemical engineering department, and started studying molten salt reactors. And as we did research on these reactors, I realized that they had an incredible capacity to solve some of the major challenges of nuclear that the other reactors just did not.
Okay, I mean, so the molten salt, is that used instead of control rods, or how is it used in a nuclear reactor?
So molten salt is actually a fuel. And so typically in a nuclear reactor, what they do is they take solid fuel rods, they get uranium dioxide, and they compress it into pellets and then stack it in a tube of zircaloy and get a bunch of these tubes together, and the uranium splits and water flows on the outside of those tubes and cools it off. Well, in a molten salt, instead of having a solid fuel, you actually dissolve the uranium, or even thorium is a possibility, directly into a salt that is melted. And this salt is an ionic liquid, meaning it has really strong positive, really strong negative charges that disassociate when it melts. And the benefit of this is it bonds chemically to the fuel and to all the leftover fission products when that uranium splits. And so it's really good at trapping everything inside the fuel form. Whereas in a solid fuel, when you cause that fission, things bubble out. It could interact with the water and dissolve into the water. And so you need lots of layers of containment to keep all those fission products and radioactive particles inside the fuel rod. Whereas for a molten salt, you don't need any of that. It's chemically bound quite tightly and quite, not permanently, but for a very long time, basically the life of the storage. And so you can end up simplifying your reactor dramatically because you don't need a lot of these containment layers and containment cladding and things like that, because the salt does chemically what all of our man-made barriers do mechanically.
So it carries what? It prevents the reactants from migrating too much?
Yeah.
Does it hold them in place and space them out so for
Yep.
the most efficient...
That's right. That's right. It'll hold in place. And, what we worry about a lot in nuclear energy production is the dreaded meltdown reaction. And in the solid fuel reactor, what this essentially is the cladding and the solid parts of the fuel melt. And what that means is then the fission products are free to escape. And then they get into the water, and then they potentially will leave the reactor. And then you have this potential dose of radioactive particles that enters the environment. And that's what happened at Fukushima, and that's what people are really concerned about. Well, in a molten salt, in that scenario, one, the fuel is already melted, so a meltdown doesn't make sense. Two, because those fission products are so tightly bound to the salt, they're not getting out. And in fact, even if the salt is leaked or removed from the reactor, those fission products still stay in that salt. And so if you use the right kind of salt that has the right kind of melting freezing point and that doesn't dissolve easily in water, then you end up with a reactor where you're not spreading fission products everywhere. The other thing is, for traditional reactors, there's going to be high pressure. And so a high pressure reactor vessel means if anything goes wrong, if there's a leak, that pressure wants to get out, and you'll have a force that will want to blast things out of the reactor. In the salt reactor, it's actually at atmospheric pressure or even slightly less, and so there is no force or impetus to push anything out of the reactor. And so instead of having an accident scenario where you worry about releasing radioactive particles, now in these salt reactors, everything stays trapped and bound no matter what, even at really high temperatures, even in earthquakes and floods, et cetera, because it's trapped chemically in that salt. So that's really the purpose, is to make sure you're not releasing any of those radioactive particles to the public.
Oh. Does this work for uranium reactors, plutonium, thorium? What radionuclides are good or not?
You can use any fuel. And in fact, one of the unique advantages of a salt reactor, a molten salt reactor, is it's one of the only fuel types that works really well with thorium. Thorium is actually not a fuel in and of itself. What it is what they call a fertile material, meaning it will absorb a neutron and then become a fuel. And so it'll become uranium-233. And because it absorbs a neutron before it fissions, it's really tough to use that as a fuel in solid fuel, because then you have to constantly be mixing the rods around to get the fuel and the fertile material in the right places to keep the reaction going. But in a salt fuel, because it's a liquid, you have these convective motions, kind of like a boiling pot of water where the salt's moving all around and it self-mixes and regulates the concentration. So it's actually really, really, really effective at using thorium, whereas we tried for a long time at MIT to make solid fuels work with thorium, and it just didn't work well. And the advantage of thorium is when you're using thorium, you don't make plutonium and americium and curium and these components of nuclear waste that last 300,000 years. You can completely avoid that, and you essentially just have what they call fission products that will only last 300 years at most. So it makes the fuel much less radiotoxic to use thorium, and you can really only use thorium in this molten salt.
But if you need to reconstitute the molten salt carrier and put fresh material in it, can you do that? Is there a way to...
Yep. And in fact, essentially what you do to make this fuel is you simply grab the chunk of uranium and you drop it in, and it dissolves in the salt. And if you need to refuel, then you just grab another chunk of uranium and you drop it in. Now, eventually, what happens for typical nuclear reactors is the fission products, or those leftover pieces of the split uranium, build up. And some of them will actually absorb neutrons, and so they'll actually prevent neutrons from getting to the fuel and causing fission. So after some period of time, these fission products will, what they call poison, or in other words, stop the fission process from being steady state, and it will shut down. And that's what we consider end of fuel life, or solid fuel reactors. And that's when we have to either put new fuel in, or shuffle it around or something like that. And it turns out there's actually still roughly 95% of the good uranium fuel is still in our spent fuel rods. There's just so much fission products in there blocking it, we can't keep the fission process going. And so when we're throwing away this used nuclear fuel or putting it in Yucca Mountain or storing it in barrels, most of it's still good fuel. We just can't run the fission process with those fission products in there. Well, one of the advantages of a molten salt is because it's this ionic liquid, it's very susceptible to electrochemistry. So we could actually take that salt after it's run, when it has all that mess of fission products in there, and we can stick a couple of electrodes in there and run a current and voltage. And depending on the current and voltage, we can pull out the fission products, about 50 different elements, one by one by plating them on one of those electrodes and then pulling it out. So in other words, we now have a way in situ to be able to pull those fission products out of the salt so we can stick it right back in and let it keep burning the uranium because we're getting rid of the things that are blocking the fission.
Yeah, I guess you can modulate the reaction rates, the products created. I guess if you had to do an emergency shutdown, there's probably a way to inject something into the mixture that would rapidly shut everything down, is my guess.
Yep, absolutely. Yep. In fact, depending on the design, there are probably half a dozen different molten salt reactor designs, but almost every design has anything ranging from something that's like a control rod or a strong poison that you can inject, or dropping liquids in there that would provide a poison. And by poison, we mean something that absorbs neutrons so the fission stops. And so most designs have a variety of different ways of modulating that reaction and shutting down the reactor in the case of an emergency, or even just if you want to shut it down to do anything with the reactor itself.
Yeah, it sounds amazing. What about the heat capacity of the molten salt? It must be very high. And I would guess once it's heated up, it retains its heat for a very long time. But in the nuclear reactions, if they create quite a bit of heat, is it difficult to get the heat off so it doesn't get too hot and maybe accelerate the reaction too much?
Great question. So let's break that down into the parts. First of all, yes, salt does have a good heat capacity. It does absorb a lot of heat, and it can get very hot. In fact, it doesn't even melt till about 450 degrees C at the lowest viable molten salt fuel. And it doesn't boil until about 1200 degrees C. So it has a massive window of operation, which is really nice. One of the really strong benefits of a molten salt reactor is actually a power feedback when it comes to temperature. So in other words, if you can't get that heat out, and by the way, how well you get that heat out really depends on the design. If you have a design that is really, really effective at transferring heat, you have a lot of conductive surfaces and a lot of convective regions, so it's easy to get that heat out, then it's not an issue. But if you do end up not able to get all the heat out and it heats up, well, what happens is the salt actually expands significantly with temperature. And when it does so, the fuel particles are now further apart, and there's less of them per volume because you've expanded this fuel, which means that there are less fissions, which means it will actually slow down the process. So it's almost like having cruise control on your reactor. As it heats up, then that fuel will expand, the fissions will drop, and it will cool itself back down. And the same will happen in reverse. If it cools down, then the fuel will be more dense, there will be more fuel per volume, and will actually increase the fissions and start to heat back up. So that's one of the unique properties of molten salt, is the physics of that salt facilitate having a really, really, really regulated reactor without any need for controls. And in fact, that was one of the appeals of the original molten salt reactor, was they found out with the very first one they built, the aircraft reactor experiment, or the ARE, that they could leave it alone and didn't need any control rods because the salt would regulate itself.
Yeah, that's really cool. If you have different geometries in the reactor, let's say the molten salt is a foot deep, are you going to get temperature variations? Like at the bottom, it'll be a lot cooler than the top, or by circulating it, you don't have that problem?
You could have that problem. So there's a variety of ways to build these reactors. One school of thought for building salt reactors is to actually have pumps that circulate the salt. And so you would eliminate this temperature stratification you're referring to just by convective forced flow, right? You have a pump that's pushing things from top to bottom, etc. Another variety or school of thought, and it's the one that we kind of looked at for these micro-reactors, is to not have a pump for a variety of reasons. Pumps that pump molten salt fail easily. They're difficult to manage and maintain, and salt is just difficult because it's a very hot, very corrosive fluid. But if you don't have a pump, if you design it correctly, you can create what they call a natural circulation flow, where you heat it up at the bottom and then it gets cooled off at the top. And it's almost like a hot air balloon that will rise and fall as the stuff inside heats up and cools down. And so you have, in essence, the salt that's undergoing the most rigorous fission at the bottom will heat up the most. The density will go down. It will start floating to the top. As it goes to the top, it passes the heat exchanger where you're trying to remove heat or electricity from. That will cool it down. The density will increase and it will drop right back down. And so if you design it properly, i.e. having a heat source at the bottom and a heat sink at the top, you can actually induce natural circulation flows that will facilitate transporting that heat to the heat exchanger and out of the reactor.
Very, very interesting. The source material you use for this? Is there any possibility of using waste? Is the system more tolerant of a less clean feedstock? So you can use more sources?
Absolutely. Absolutely. And the restriction there is not on the technology, but on the regulations and the licensing for handling and using that waste. There are some pretty stringent restrictions on reprocessing or reusing nuclear waste as a fuel, but certainly the capacity is there. In fact, one of the first molten salt companies to attempt to commercialize a product, Transatomic, actually had that as one of their flagship goals and statements, that they were going to take the legacy waste from light water reactors and use that as fuel in their molten salt reactors. So it's definitely a possibility.
Okay. Are there any reactors where this kind of a system wouldn't be amenable? Can existing ones be retrofit?
They could. And what it depends on is how you've designed your core and the kind of neutronic interactions that are taking place, and also the size and the purpose. So for example, the reactor that we have designed is a micro-reactor, meaning we are going for the smallest possible size. The core itself is about 4 feet by 7 feet, and it makes 12 megawatts. So it's a very power-dense little core. In order to put in spent nuclear fuel, because there's things that are not necessarily the fissile material in there, you would need to have more of it, which means you'd need to have a bigger core. So if you have a core that's designed to be big in the first place, it's not a big deal. If you have a smaller core, it's a little bit more of a challenge. You'd have to increase the core size in order to fit the extra stuff that comes with the waste to make that happen. But it certainly is a possibility if you plan with a little foresight. Retrofitting would be a little bit harder if it's a small core. If it's a big core, not a big problem.
So far, are there any downsides to the system? It sounds like a huge step forward.
It is, and I've told people before, I've worked on every kind of reactor that there is, and in my opinion, the salt reactor is kind of like the equivalent of the silicon chip in the computer industry. It really is an advancement where we can solve a lot of the major problems people are concerned with, potentially, with this salt reactor. One of the big drawbacks, and the big drawback that they saw back in the 60s when they ran those experiments, was that the salt can be really, really, really corrosive. And so that can be a challenge. One of the things that we've done at Alphatech, which is the company that I helped to found to do this small micro-sized reactor, is we actually figured out the source of that corrosion within the salt. Turns out it's dissolved oxygen from being exposed to air and water. And we figured out how to remove that oxygen and also some hydrogen, which creates oxides and hydrides that causes that corrosion. And we've demonstrated on a lab scale that when we remove those things, the salt becomes much, much, much less corrosive.
Oh, that's great. What about the radioactive materials ionizing the salt itself? Yeah, if you have like a potassium salt, could you make radioactive potassium, and would that affect it at all?
Yeah, great question. The potassium already actually comes partly radioactive. That's why bananas and even people are a little bit radioactive. And some of those components in the fuel are likely to absorb neutrons. The nice thing is the binding energy of the salt is so high that you're not going to go through radiolysis, or in other words, breaking apart molecules, which means they're pretty stable. You'll create some isotopes for sure, but the nice thing is most of those isotopes that you're going to be creating, like the potassium you mentioned, although most reactor salts don't include potassium because it's a good neutron poison, but other things like the chlorine or beryllium or other components may undergo interactions. Most of them will not be highly radioactive, but rather they will probably do things like create helium or tritium or things like that. The things that are created, again, are bound to that salt, and we can use electrochemistry to pull them out. And most of those radioactive components actually are valuable. They're needed for experiments at labs. They're needed for military purposes, not weapons, but for scoping and sighting and irradiation of food and things like that. So it turns out that nuclear waste is about 50 different elements, 52, if I remember right. And most of them, if not all of them, have a price tag. The challenge is in solid fuel, separating them out is really difficult. You'd have to go in and grab the rods, which are highly radioactive. You'd have to chop them into pieces, dissolve them in a variety of different acids to separate all these different components out. And it just isn't really viable in terms of price. It's not economically viable compared to just grabbing new fuel and throwing it in. But if you use the salt and you use the electrochemistry to separate these pieces, you're looking at things like molybdenum and zirconium and neodymium and europium, so a variety of rare earth elements and precious elements and medical isotopes and commercial isotopes. And most of them have a price tag ranging from zirconium, which is a few dollars a kilogram, all the way up to moly-99, which is a medical isotope that we use daily in our hospitals, and that's $30 million a gram. And so for the most part, you could actually separate all those things out and sell them and be left with no waste. Even though some of them are radioactive, they still have a value and are used either in the medical or industrial complexes.
But even with the more expensive radioisotopes, it's still not worth it to process a lot of spent fuels?
Oh, it's definitely worth it. And a lot of molten salt reactor designers are purporting that that's what they want to do. The challenge, again, is not cost when it comes to molten salt separation of the waste and selling of these isotopes. It's the licensing and the regulations. Right now, there's not any way that has been codified in law or that has been given as precedent by the regulators to do that. And so a lot of these salt companies, Kairos is one, TerraPower is another, Alphatech is the one I helped co-found is another. They're trying to figure out the regulation and trying to talk with the regulator to figure out a process to, first of all, license and operate these reactors, and second of all, to do things like process and recycle the salt so that we can get those valuable isotopes out and sell them.
So are there in production reactors that are using molten salts right now?
Now, right now, we did have one that we ran back in the 60s. Oak Ridge ran that for 4 or 5 years, did a great job, and demonstrated all the concepts beautifully. But it got to a point where the U.S. government decided we could only afford one reactor program, and Admiral Rickover with the light water reactor was very persuasive and convinced them that he had done this in subs and reactors, he'd be able, or subs and ships, and he'd be able to bring it to land, and that it was very good at making weapons. And so the light water reactor was selected. And now in hindsight, a lot of people are saying, hey, let's take another look at the salt reactors. Several countries have been recently very interested in making this work. Like China has a big molten salt project that they are trying to make happen, and Canada has been interested, and Indonesia is working with the U.S. company to try and make it happen. So there's a lot of interest in putting them together, but right now they are not, primarily for that reason I cited, that the regulation does not yet facilitate that. And so we have a long, not only engineering project, but a regulatory and legal work that needs to be done before we can see these commercially developed.
Well, why not approach France? They use a lot of nuclear. Maybe they'd be more amenable because their law structure probably allows for a lot.
They do, and that's a great possibility that some people have discussed. The challenge now, though, is if you're a U.S. company that's developed this IP in the U.S., then that's considered an export, and the export control laws for nuclear technology are kind of large. And so we really have, pick your poison. You either have a lot of regulatory work to do to license a reactor in the U.S., or you have a lot of legal work to do to export that technology to another country. So
essentially, instead of molten salt reactors, you have like molten molasses reactors that can go nowhere so far.
That's about right. Now, that being said, some of these bigger companies like Bill Gates's TerraPower and Kairos, backed by Silicon Valley millionaires, they are moving forward and talking with the regulator and having great success in negotiating pathways for moving this forward. If you've been looking at the news recently, there was a lot of hubbub about plant that was being built in Kemmerer, Wyoming to replace a retiring coal plant, and that was Bill Gates's plant. But in addition to that plant, he has a healthy molten salt reactor that his team is developing called the McCree that they're working with the regulator to be able to license and build as well. So progress is being made. I would say probably a decade ago, almost nobody knew about these types of reactors, and there was very little enthusiasm or interest. But in the last decade, there's been a big swing, and now DOE is providing quite a bit of funding. There's about a dozen different companies just in the U.S. that are trying to commercialize these things. And I think it looks like most people are recognizing their potential and are working with the legal and the technical challenges to make them a reality within, I'd say, probably 10 years.
Where is this going to show up first? In a submarine or in a land-based reactor plant that provides energy to a region?
I would say probably a land-based reactor for a couple of reasons. One, the Navy is very, very good at making their light water reactors. They work well, and I don't think that they have any reason to innovate or rock the boat, so to speak, not intended. But I think that their advantages include not requiring any water. And so if you look at a map of where nuclear reactors were built historically, most of them are where population and water is located. You don't have a lot of reactors in the West or the Southwest for that reason, except for a couple that are on rivers. And so I suspect that this would be a nice solution to those regions that would like to have nuclear power but don't have a lot of water. They don't need the water. Plus, they address a lot of issues. For example, the salt is so hot that even after you extract all the energy you can for electricity, it still is at about 550 degrees C. And there's so much heat in that salt that you can extract the rest of that in what you call a bottoming cycle and use that to desalinate water. And in the West, California, where water is a big deal, you can desalinate water with the waste heat after you've made the electricity from these reactors. And that's a huge benefit. So I suspect there will be a strong desire to have some of these reactors in the arid West, both for the electricity, but also as a means to produce desalinated water for the populations.
Well, the other thing, too, is for safety. So you could say not only are these more safe, lower pressure, et cetera, blah, 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 but if we put them in an environment like Arizona or Death Valley or whatever, if there's a spill, it's not going to go anywhere. And people don't live in those areas very much. There's no waterways to carry it away and poison the ecosystem. So for many reasons, it seems like ideal to be in those places.
That's right. That's exactly right. And I've seen that those places have a huge enthusiasm for these types of reactors. So I suspect it would be something like that that will be the source and the initial spot. Now, that being said, depending on what happens with the regulator, it's very likely that internationally or the DoD might end up developing these reactors for some placing them at their locations. But I think eventually they will make it to the domestic West and arid locations where that makes a lot of sense.
It'll be crazy. I have no idea if the numbers work out at all. But, what if like Intel and AMD ended up using a reactor as like literally the supply of all the electricity to run their fabs? Where, like what if you literally supplied like an industry like that? That would be amazing.
It would. And they've actually been in conversations with us and other reactor designers. There's a huge conversation going on with multiple reactor vendors and these data centers or chip producers or other fab systems because of the amount of heat and energy and electricity that is needed. And right now, so a little bit of forecasting, because of electrification of vehicles, because of this AI data processing, blockchain craze that we're going through, it's anticipated that the demand for electricity in this country will increase by 2 to 10 times. That's an astounding number that I don't think we can even comprehend. Every power plant that's running that we've built, we'd have to build that again and again and again. It's just an endeavor we have not undertaken in this country for decades. And so they're running into a situation, these data centers, they tell us that because of this potential increasing demand, because of their demand, they're approaching utilities, and the utilities are saying, well, you have to pay us money now to reserve a spot in line so that you can pay us for the electricity 4 years from now. And it's really frustrating to them that they just don't have any source of electricity. So they turn to nuclear companies to say, forget utilities, can you provide us direct power for these data centers, for the fabrication facilities, for whatever. So I think your comment is insightful in that I suspect that's going to be a large customer for some of these reactors because they need so much electricity and they're not going to be able to get it in a timely fashion from utilities these days.
Yeah, also, what about you using one of these reactors to power, fusion experiments, maybe a fusion reactor too?
Absolutely. Absolutely. In fact, I've long told people that I think that the military had it right, that fusion and fission make a great hybrid. Let's not do it uncontrolled like they do, but I think that powering a fusion reactor and assisting in fusion and reducing the energy requirements with a fission reactor is probably a really smart way to go. The only challenge there is now you have two very uncertain devices that you've got to engineer and put together instead of one, which of course increases the difficulty of licensing and engineering exponentially.
I'm surprised there's not more of a push for this. It just, coal plants wouldn't have to be online. It would be a cleaner source of fuel. There's much lower, risk of things going wrong. You can do desalination. You can supply power to towns. Why is there still such a problem?
So that's a great point and a great question. I think that the interest is growing. Like I said, over the last decade, I've seen substantial increase in the interest. The barrier to entry is the regulation, either from exporting or from licensing here in the U.S. And that is, to give you an idea, there are exactly 2 companies that have gone through the licensing process and successfully licensed any nuclear reactor design. It was the traditional light water reactors. One is Westinghouse. It took them 20 years and $1 billion and basically drove them bankrupt. And the other is NuScale. And it also took them 20 years and $1 billion. And they're not bankrupt, but they're struggling for customers because the price of their power increased so much because of the regulatory burden. And so the challenge to overcome is not PR, it's not technical viability, it's not even demand. It's really getting a reactor through that licensing process because we're not good at it. It takes too long. It's very expensive. And so that's where a lot of the big money effort has been going. And once that hurdle has been overcome, or once we figure out how to license these reactors without driving the company bankrupt. I suspect that there will be a lot of orders for these molten salt reactors among the communities that need this power.
Yeah, it seems like the industry needs an incredibly wealthy and influential patron in order to get there.
Right. And they had that in Bill Gates, and he has been successfully working with the regulators. Also, I mentioned Kairos Power before. They also have some wealthy backers from Silicon Valley, and they have been very successful as well. In fact, they were able to get a license for the very first non-light water reactor ever, their Hermes test reactor. It's just a small little test reactor cooled by molten salt, but it is still nonetheless a successful prototype license. So I think that those big backers are doing exactly that. And all the other smaller groups are sitting back saying, hey, if you guys want to carry this, heck yeah, we'll let you take it. And then we'll jump in once the licensing process is established. So.
Okay. Well, very good. Matt, this is fascinating. Where can people keep tabs on it and, see what you're doing, what the other players in the industry are doing?
Yeah, great question. There's lots of YouTube videos about molten salt reactors. A lot of people who are developing them are really excited about it. You can Google search almost anything nuclear, and if you want regular updates on the industry and on the state of nuclear power as a whole, NEI, the Nuclear Energy Institute, is a great source of information about everything current and all things nuclear, and you can search among their information, particularly the molten salt stuff, at any time. So,
well, excellent. Thank you so much for coming on the podcast, and I really appreciate you being here.
Happy to be here. Thanks. It was a great opportunity.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.